This is section 14.8, Introduction to Mass Spectrometry. Spectrometry is the study of matter-energy interactions, whereas spectroscopy, from the earlier part of this chapter, when we were talking about IR spectroscopy, was a study of light-matter interactions. Spectrometry is a study of matter-energy interactions. And why is this going to be important? Well, it's all going to center around one very simple mechanism. Say, for instance, you have a molecule like ethane. Okay, you have two CCs bonded together in a single bond. If you attack that molecule with an electron beam, what you will do is you will knock an electron out of the bond in between the two carbons to leave you with a formally positive molecule and the electron. And what happens is, or not what happens, but we call this ion that results from this electron beam attack M+, or the parent ion. Now the molecule there, you might imagine, isn't very stable, the one with one electron in between the two carbons. So what actually that structure probably looks like is this, where you have the parent ion actually formed of a carbon-centered radical and a carbocation. And it's this carbocation that we can actually detect using mass spectrometry. So I'm going to show you what a mass spectrometer is and the principle of its working, because it's very simple actually. So in mass spectrometry, you have your product that is placed on a tiny, perhaps a tiny plate, or perhaps you inject a solution of whatever molecule you want to analyze. And after injecting the solution that you want to analyze, it is carried through the instrument using gas inflow. So there's a stream of gas carrying the molecules. And as soon as it takes off, so to speak, then there's an ionizing filament here that causes the ions by electron beam or some other type of ionization. Once it does ionize the material, the now ionized carbocations go through an ion accelerator that helps to speed up the ions as they fly through the gas flow, in addition to a small opening called a slit that's used to focus the beam. Because in this cartoon, it's drawn as a line. And that's really how we want our ion stream to be, one nice line. Because eventually it goes into a magnet where you have one side the north, for instance, and one side the south. And depending on what's called the mass over charge, M over Z, or in this case, M over Q, the ions will be curved in a different trajectory. So you see here that the lower ions were curved just a little ahead of the higher mass ions. And by this principle, you can actually find out what ions are present in your sample because you set the detector some plate, I don't know, say here, and then the ions physically collide with the plate. And when they do that, then you could detect where on the plate they collided, and you can generate data that tells you what the mass of these ions that you collected were. So what we can say then, and what is really useful about mass spectrometry, stop sharing the screen, is that if we have something like methane, and we take methane and we hit it with an electron beam, we'll generate the parent ion that has a mass over charge of 16, because methane has a charge, a molecular weight of 16, and it has a charge of 1. So mass over 1 equals 16. But then, just like we talked about before, you generate a radical and a carbocation. Well, there's only one radical to make, and that's hydrogen radical and the methyl cation. So this new cation has a mass overcharge, m over z, of 15. And so we can carefully record how much of the m over z equals 15 and 16 in order to establish differences in molecular ion fragmentation. And these differences in fragmentation are going to be how we can analyze much more complex molecules than just methane. And this was section 14.8.